Part 2, fermionic state cell models and spin structures.
Okay, so
I guess
I'm going to discuss two different topics here, and they're both related to spin structures, but first of all, I'd like to explain how Bostonization works in two spatial dimensions, one time dimension. It's an unusual thing. It's an material generalization of the Jordan-Wigner transformation in 1 plus 1 dimensions. But on the other hand, I'm going to explain other applications of this idea, the classification of short-range integral phases of fermions. And maybe I'll start actually with the second one, because one can actually get quite far in this discussion without knowing anything about this Bostonization business, just by thinking about fermion and what sort of physics you can have in a bulk or a short-range integral phase of fermions with some symmetry. So that actually explained in my recent paper with the Ryan Thorngren. Let's see. Give a reference. So which tries to extend, well, in this paper we're discussing how to classify fermionic short-range integral phase of fermions with some finite unitary symmetry. Phases plus finite symmetry. G, just sort of point symmetry, doesn't act on space, it just acts internally. Usually it's a unit system. Meaning that if you have time-reversal symmetry, it acts by anti-units, which is trying to maneuver space, and we don't allow for that. So, now, the answer is no. Well, so a priori, such if you want to fix a symmetry group, you can ask, okay, how many phases of fermions are there with the following property? Very stringent. First of all, you want the partition function on any space-time manifold to be non-zero, basically it's a phase. And second, you want the Hilbert space on any spatial, compact spatial slice to be one-dimensional, not a degeneracy. That's very stringent. So, and that's why we can classify such things at all, because we didn't try to restrict such things, especially the degeneracy is especially important. Actually, well, so not generous, because typical, well, these are called usually non-fractionalized phases when it comes to degeneracy. So we do have degeneracy then in some topological field theory, in some number of dimensions, and essentially help us to classify dimension higher than 2, from higher than 2 space. But here it's sort of like almost trivial topological field theory. Supposed to classify that. Now, for bosons, actually the answer, well, the answer actually is not even trivial for bosons, but non-triviality only starts in especially high dimension. So in physical dimension, like 1, 2, 3, the boson's problem essentially solved by so-called group cohomology approach. Such phases in the bosonic case, well, either bosonic harmonic case, they form a abelian group, because you have two such phases, you stack them together, you're going to get another phase of this sort. The time reversal of such phases is sort of inverse, so there's a abelian group structure there. And for bosonic theories, I have to let you know. Well, I usually will write this net, but this for D, this space and dimension being like 2, 3, and 4, which is, well, in higher dimensions actually not true, but higher dimensions are all on academic approaches.
Is the space-time dimension?
Yeah.
Okay, so it's,
Actually, starting with 5 dimensions, it's already not true. In 5 dimensions, there is some bosonic phase, even for a trivial symmetry group, which is shorter than tangled and different from the trivial.
so is the integer quantum Hall state, so in just in 2 plus 1 dimensions, is the integer quantum Hall state
Well, I'm
non-trivial?
well, I'm assuming finite symmetry, first of all.
I see, okay. So no U1.
No, you're well. One's a bit more difficult. But in 5 dimensions, there's something non-trivial for trivial symmetry. There's some phase which is no degeneracy on any spatial, 4-dimensional spatial slice. But with the, nevertheless, with some 5-dimensional space, the manifold projection function is not 1. It's some phase. So this thing exists in 5 space-time dimensions, but it's only of academic interest. So in all dimensions, that's all there is in the bosonic fields.
No, but it's still interesting because what you're saying is that there is some refinement of group homology which coincides with group homology.
Well, yeah, in general, the correct answer involves the cobordism of the classifying space of the group instead of, well, this is just usual cohomology of the classifying space of G, right? Instead of that, you can take oriented cobordism.
I see. So you're saying there is a generalized homology theory that actually calculates the correct thing,
Yeah.
and it just happens to.
And it's just cobordism. In general, it's cobordism, and then just all dimensions is the same. Anyway, moreover, more concretely, I can actually exhibit explicit lattice models according to every class here. So this is important. Because having an abstract answer doesn't really help you unless you can write models and actually explain what this class means physically. But I like to do the same thing with fermionic phasors. To explain some sort of physical reasoning which allows you to sort of guess the answer. You can derive it, but just guess the answer. So let's start with dimension, space and dimension T. So in general, so in 2 dimensions, usually the way people approach this question is by looking not only closed manifold, but manifold with the bounds, an interclosed. Suppose it's 1-dimensional space, right? People usually say, well, consider Hamiltonian system on the 1-dimensional space with a boundary, that's an interval. And then in this case, well, the advantage of this is, when you have no boundary, there's a circle, then there's only 1-dimensional vector space, nothing interesting can say about it, basically. The group acts trivial, it's invariant because its symmetry is unbroken, and that's it, there's nothing else to say. So you cannot tell the difference. But if you have boundaries, you have zero mode, some, first of all, the space is not degenerate, you have boundaries generically, and there is some action of the group on this Hilbert space, which can interpret as actions themselves, all progress living on the edges. You can look at that this way. But you can also look at, you can give about description, sort of. So I prefer that, so we can just look at the about description. The point is this, so, well, first of all, we have fermions can have sort of 2 spin structures. Either fermions make them periodic or antiperiodic in the circle. If they're periodic, it's called Ramon structure, and if it's periodic and Ramon structure, it's mathematics called the non-boundary spin structure, and a term that's periodic. And when antiperiodic, it's called Neuer-Schwarz structure. And well, by assumption, it doesn't matter which spin structure you choose, you still have only 1-dimensional Hilbert space. That's fine. But you can, in fermionic case, you can ask, okay, fermionic or bosonic? Essentially, by convention, in the Neuer-Schwarz sector, the ground state is bosonic. So there's no degrading operator minus 1 over F. So this means ground state is eigenstate Benjamin plus 1. But then you can look at the Ramon one in that case, is it fermionic or bosonic? And that gives you already 2 possibilities, even without anything. There's some parameter gamma, which is either the 0 or 1, which does already distinguishes some phases. So gamma is Z-mod 2. So that's parameter is quite famous, discovered I think by Kitaev. So Kitaev again looked at this situation where they have boundaries and said that the boundary of this chain you can have some zero mod which are Majorana, like one Majorana 0 mod 1 and not one on the other end. And they together they make a fermion, so you get the double generator. So you get like a Fock space for the representation of the Clifford algebra with one generator, which is great in that. So find which comes from a Majorana 1 and another. That's a non-trivial chain, a system which corresponds to gamma equal to 1. And the trivial corresponds to it, which is not degenerate symbol. But when you glue these systems on a circle, you don't see any degeneracy, but you see one difference. When there's some way to refer to spin structure, and when you look at this Ramon structure, the ground state is not generated, it's fermionic. So the current goes apart on the closed space. Okay, now suppose we add some symmetry group, I think. So this makes sense even when the symmetry is clearly ignored. Well, generally you can have also a gauge field. And in one dimension, the only thing you can do is you can create some hole on the gauge field around the circle. And now, again, you can put the reverse structure on a Ramon structure, but we don't really need to consider Ramon because we can determine the Ramon Schwartz. If you know gamma, the only thing you can look at really is again whether the ground state of this sector is fermionic or bosonic. And physically, we can think of it this way. So when you put this holonomy and then break the symmetry spontaneously a little bit, then there's a domain wall here somewhere. It doesn't matter where. This domain wall is it's a zero-dimensional guy. It's a particle, so one try to assign the Fermat number to it. So think of this whole Fermat number is concentrated here. So you get them with zeta of G, which is Z mod, which tells you whether for any particular holonomy the state is fermionic or bosonic in the Schwartz setting. And for Schwartz, for Ramon, we need new information just gets shifted by this gamma, the same guy. So it doesn't make a difference. So now this function from group to Z mod 2 is actually homomorphism because we have two such domain walls and merge them together. It's going to get the homomorphic domain wall for the product of G and G primes. The conservation of fermion number, in other words, requires this property. It's a homomorphism from G to Z2. Okay, so we have another parameter. And the third parameter involves properties of the domain wall.
So do I have a degenerate ground state?
No, there's only one ground state for any particular G, and that can be fermionic rather than bosonic.
But can I have different ground states for the different G's? I mean,
but you cannot compare them somehow. For a given G, there's some ground state, that's it.
okay.
For another, there's another ground state. And we can compare for the fermion number with the bosonic fermionic. So for a trivial,
You're talking about for different capital G's, not for different little G's.
for different little, very, very little G, it's a domain wall. For every element of the group that defines the domain wall. The domain wall can be either boson or fermion. And the domain wall, I mean, really, I break some. Okay, finally, suppose I decided to compute a function on some two-dimensional manifold for this theory. Now, I should be able to do it for any background gauge field. It should give me some number. By assumption, this number must be just a phase. So, how do they do that? Well, again, I can try to break symmetry spontaneously a little bit. And then I'm going to the gauge field is sort of concentrated on these domain walls. I'm going to have this network of domain walls on my space-time. There was a network of domain walls. And then it's always trivalent graph and resolve some polyvalent intersection of trivalent ones. And so how do we compute partition function? Well, this particle propagating, and when they propagate, nothing interesting is happening. But when they merge, I might have to sort of phase. So it's scattering matrix. It's called alpha of GH. This is the domain wall by this is by H. It's an alpha of GH. And then the partition function is going to be the sum over all these points, or vertices of the chart of the graph, and then give me my partition function. So this is going to be variable in R mod Z, that is which should be 1, and then we're going to the partition function is the product over all vertices of by R alpha. Now, and this guy is like a constraint, kind of like this one. So there are two ways to explain this constraint. One way to explain the constraint is, suppose I have this network and some picture like this someplace. Now I can reconnect the network somewhere like this. That basically responds to some gauge transformation. It doesn't work.
It's become a tradition.
Okay. Let's go back there more. And well, this Z better be invariant with this gauge symmetry. And that gives some condition on alpha. It's a 4-term condition, right? The sum of these two alphas will equal the sum of these two alphas. And that can be written as some, well, this is called a Tuka cycle on the group with variable number of Z, and this condition for the flow, limit condition alpha. Shorthand for this. In other words, alpha, now, first of all, alpha is not uniquely defined because you can redefine these phases by, say, assigning something to the propagator. But then it doesn't change C. It responds to gauge transformation. So it's written over the class of alpha in H2 of G with R mod H2 is physical. So, okay, so this is the situation. So this is the sort of sketch of how to classify phases in 2 dimensions. We have these 3 parameters: alpha, beta, and gamma. And alpha is an indication of the class name. Beta is H1. Homomorphism, in other words. And gamma is, well, connected to H0. Oh, sorry, it's and this is constant. That's what we get into dimensions. And there's a further tricky thing. Okay, what is the group structure of this set? So one can, some care is needed. Like, there's, suppose I stack these phases on top of each other.
So actually, so the beta and the gamma, they're completely sort of independent of each other?
Yeah. So there's no constraint. Actually, everything is dependent. Alpha, beta, gamma, all dependent. But there's something interesting happens when you study how to, put the abelian group structure here. Namely, suppose you have to stack the systems over each other. This should give another such guy, right? So what is the group law of these triples? Because of course the obvious one, right? Just try to add up all these independently. But the Fermi statistics actually makes an appearance. I'm going to explain this, but since the answer for some reason is not written anywhere, except in our paper with my students, so I'm going to propose this. The parameters themselves were actually written down by Pitkovsky and Kitaev and by Chen, Gu, Liu, and Wen, I think, somebody that studied the group law. This is the group law. This is a non-trivial correction.
So it's like a Heisenberg.
Yeah. So concretely, like this is what this means. Beta, cut beta prime of GH is simply beta of G times beta of H. So actually it means 1/2. So with my notation, alpha takes values in real numbers modulo integers, while beta takes values in modulo 2. So 1/2 here, so that it's shifted by half an integer.
So gamma completely decouples.
Gamma decouples. So let me explain similar thing in 2 plus 1 dimension. So in 3 dimensions, again, I'm going to look at the main walls. So the main wall in 3 dimensions, what is it in spatial? If you look at spatial slice, and the main wall is 1 dimension. Well, it will include tangents 2 dimension. And they all have labeled by group elements. So the first question to ask is this. Okay, suppose we broke this symmetry, so we get actually the main walls. We know that 1-dimensional system, if you forget about the symmetry, okay, so 1-dimensional system here can be non-trivial, as I discussed before. This gamma parameter tells you that a system without any symmetry can be non-trivial. In other words, this guy can carry sort of this Majorana chain or type chain. What this means is that its endpoint can carry this Majorana 0 mode. So, okay, either it does carry it or it doesn't carry it. So there's some parameter gamma of G which tells you whether it does or doesn't. Take a look at this one. Or it's homomorphism. Why? Well, because if you collide again to such dimensionals, then the corresponding gamma parameter just add up. So therefore, this must have this property. So the gamma will use NH1 over G with coefficient. Although they probability to shift from dimension. Now, okay, so let's look at junctions of domain walls. So another way to see that something you must have this condition to look at this some junction of 3 domain walls. Now, if each endpoint carries some Majorana, some number 0 modes, the net number should be 0 modulo 2. Why? Well, because otherwise you'll have odd number of Majorana modes. There's no way to quantize this with some local Hilbert space here. So that condition ensures this. So okay, so once you quantize them, they there's no Majorana 0 modes, maybe 2. Quantize them, you get some Hilbert space, and it has a ground state. The ground state is Hilbert space, which has minimum energy, but that state may be bosonic or fermionic. So details depend on the it might how you terminate them. It also may affect whether it's bosonic or fermionic, but there's some fermionic number.
So you're saying you can't have an unpaired Majorana mode there? Couldn't you have another one somewhere else?
No, but well, just some of the fact that you have this property, I'm sure it's not going to happen. But I think the point is that if you have an SPT phase, it's not in a closed manifold, there's no way to have that. So it should be some unique ground state in the locally. So we're going to listen. It's storage entanglement nature of this game, I guess.
So I have right.
Okay, so now, so there's some number here, modulo 2, which is the fermionic number of this junction. It's like in 1 dimension, spatial dimension, each domain wall is a particle. Here there are strings, but they're triple junctions of particles. So there is some number here we're going to call beta, which tells you the fermionic number. And this beta, must be set by constraint. Why? Well, imagine again this network of domain walls. Well, the fermionic number will be the sum of the fermionic numbers of these junctions. And it should be invariant in the local rearrangement of this network. So I better have this property. This 4-term property with some 2 bases from here and here. Because here there are some linear conditional cases. In other words, beta. Beta is an H2. Actually, only see the actual fermionic number here is ambiguous because you can change the fermionic ground into bosonic one by choosing the different Hamiltonian. But basically, by attaching this fermionic, some Kitaev can attach that chain to this guy. We have a formula that change this number, but that changes the number of volts here at the dotted end of it. So beta can be changed based on the co-boundary. That's what makes homology class matters. So and finally, you can ask again, think about three-dimensional space-time, and then consider what happens when we have this. So we have this. So now I have this in space-time. You have this particle, which is a junction propagating time, and then the fourth dimensional comes and sort of terminates the whole story. So now, in other words, now we have this place where 4 of these world lines terminate, which you can imagine as two schedules. So these two guys scheduled to these coordinates. Now there's some amplitude there, which you can call alpha. So there's really 3 independent G's here. There's one here, one here, this one is GH, and then the fourth one is this K, which is also independent. So they're, like if you, the dual pictures are like, it's like a tetrahedron actually. So this point, like in the middle of the tetrahedron, and each of these lines pierces the face of the tetrahedron. So this amplitude between the 3 elements, and is there any constraint on that? By the way, I guess to explain also in the dimension. So dimension is a different way to draw a constraint on alpha, the amplitude. Let's say the following thing. Consider space in the shape of a two-sphere, which is logically a triangle is sort of tetrahedron. On a two-sphere, of course, there are no non-trivial G gauge fields, non-trivial G bundles. It's a simply connected space, so all holonomies must be trivial once they're constructed, right? Nevertheless, I can still try to evaluate the amplitude, but the value is 1 if I want to get it, right? Because so you're going to have like 4 points where the manuals meet. And say here like a G, maybe H, K, and then the rest are fixed by the simply the product rule. Say this one is GH, and GH is by orientation. And I can now determine all the types of the manuals and then just compute the amplitude coming from 4 collision points. Add them up and require them to be 0 in the same condition, which are open. That's the condition. Now, you can do the same thing here. It's in case of 3-dimensional space, and it's harder to draw. We take a 3-dimensional sphere, which again simply connected so the non-trivial gauge field. But you can still consider, take a triangle using a 4 simplex. So what does it look like? Well, it's best to think about a stereographic projection of S3 to R3. So then this triangulation always is going to have tetrahedron in the center. Then we're going to have 4 other tetrahedra attached to it, to all these 4 faces, which go sort of go off to infinity, right? So total 5 tetrahedra, but 4 of them got mapped as non-compact infinite guys. And then I'm going to again evaluate. So there are 4 guys here, and alpha is infinity. And each is contribution of alpha, so now you get delta alpha equals 0 again. But in reality, this is more complicated because in this case, these particles are also forming. There's some particles which are fermions, and then when you try to evaluate amplitude, there's a contribution. It turns out when you project this diagram into a plane, some of these particles will cross. So in reality, there's another sign coming from the fact that some of these guys are fermions. The condition turns out to be more complicated. Gamma is again untouched. So overall, you get all the data. You get like alpha, which is a function of a chain. And there's an arm of Z, satisfying this condition. you have a beta, which is like this. You have this whole model. That's a classification of protocol classification for running SPT phases with finite unitary symmetry group. Now I didn't tell you what the group law is. You see, this looks more linear. It's not very obvious how to add up such things so that the result still satisfies the same equation. But it can be done, so checked that you get. Well, in this case, actually, there's more fun things happen because, first of all, this exact alpha is a bit pairs of beta and gamma. There is some entanglement already there. Stuff like that. If I add alpha, there's some horrible formula which tells you how to add up with alpha. I don't want to get into this. Anyway, so that's now. But what I just described here.
That half is just a natural embedding.
Sorry, this is. Well, yeah, no.
So it's the map from 0, 2 to the
Yeah.
circle. Unitary. It's globally defined. It doesn't involve any choices.
Yeah. Well. Anyway, so what I'm describing, by the way, is concrete. So I mentioned before that the correct description for Bosonic phase is really in all dimensions this cobordism of the classifying space of G. Now, in the Fermi case, natural gas is spin cobordism of the classifying space of G. And what I'm describing now is actually just an explicit description of the spin cobordism of the classifying space of G in dimension 3. So it's actually proved by Broomfield and Morgan mathematicians that this is actually this group, which I just described here, is nothing but a spin cobordism of BG in dimension 3. And what I said before about the two-dimensional case of spin cobordism in dimension 2.
So is that completely general?
Well, I suspect it's suggested, actually, in my paper, that my students that in general dimensions, Fermat phases plus with the spin cobordism. Now, I don't want to. We have in this paper, which I raised, we extended these considerations to 3 dimensions. Proposed similar equations from triples alpha, beta, gamma. There's some horrible equations. Conductor describe all thermodynamic SPT phases in 3 spatial dimensions. Find symmetry group G, and also conjecturally compute the spin cobordism in dimension 4 for arbitrary finite group. In that case, equations are truly horrible. I don't want to see them.
So the spin cobordism groups for certain finite groups are not.
Like, yeah, funny thing is, mathematicians studied spin cobordism in all dimensions for some special finite groups. So here we're trying to
So not for all groups, but in
for all groups, but in some low dimensions. For some reason, there's no resulting conjugation which would help us.
But for certain finite groups, they are
Yeah.
general.
Okay. So that's all I wanted to say about these classification of fermionic short rectangle phase. But then it's just like it's actually rather non-trivial to generalize to the case with time reversal symmetry. That is because the case when everything is unoriented. So in 2 dimensions we did this, but it's not obvious. Not entirely obvious. Okay, now I want to address the orthogonal subject, namely Bosonization in higher dimensions. So, it's not completely orthogonal, but for example, this answer for dimension 3, that is spatial dimension 3, spatial dimension 2, can be also, well, what I didn't do, I didn't actually construct explicit models for these phases. And it turns out that one can do it using this Bosonization trick. Now, paper with Gayotto, actually, it's another paper here. Gayotto and Harvard. Quick, just right there. So I want to focus now on 2 plus 1 dimensions, spatial one time, and then I want to explain this Bosonization in this topological context. I want to describe approach to classifying topological phase of formals, not necessarily short-range rectangle anymore, but via their Bosonization. So I want to explain, actually, first of all, what is the, again, in more detail, what does Bosonization mean in 2 plus 1 dimensions. So let me start with the analogy of 1 plus 1 dimensions, so which suggested this whole story. So 1 plus 1 dimensions is a well-known correspondence. We have bosonic systems with Z2 symmetry, and fermionic systems. Well, we have the fermionic pairs operator, which are this way. Takes values. Well, it's an operator Hilbert space with eigenvalues plus minus squares to 1. So it's paired. So they look very similar. The difference is here we allow degrees of freedom on different sides which are anti-commuting rather than commuting. And so there's different systems, but there's a map from one to the other, one-to-one map. It's not an equivalence again, it's different systems, but now there's a one-to-one map between these classes of systems. So how does it work on the level of Hilbert space? Well, we have a bosonic system can have a holonomy around the circle, which is either +1 or -1. Think about Z2 is plus or minus 1. And it's usually called untwisted sector, this is twisted sector. And then you can further decompose every sector into even and odd space with respect to the action of the group. So here I'm not assuming that I'm dealing with any short entangled phase, so you can have both ground states which are odd under the group and even under the group. Not all of them are very. But in general, you can just consider some bosonic system, topological, based on the genus of the ground states, both here and there, and the decompose into even and odd ones under the Z. So in harmonic case, it's a similar situation. We have now Neuer-Schwarz and Ramon-Stocker. And again, you can decompose in each sector the states into even and odd ones. And again, since I'm dealing with short-range entangled phases, now we can have many different ground states, many different pairs here. So, as well as there. Now, what's the connection between the two? So the most naive thing would be just say, well, maybe this corresponds to this and this corresponds to that. It's not as simple though. In reality, there's some more what we have to do, we have to decompose again each Hilbert space into even and odd ones here and even one there, or we'll have 4 spaces then. And similarly here, and there is some move. One component is moved between here and there, so it's a bit tricky. I'm only going to focus on this. The important thing is that the fact that the holonomy is taking values in ±1 on a circle suggests the relation with the fermions.
So it's just the Jordan transformation.
One can, and then, yeah, this is Jordan transformation. In 2 dimensions, what do we have here? We have some bosonic system, fermionic system, same manifold. How we come to okay. So in the harmonic case, when we look at the Hilbert space, again, it has even and odd sectors, right? So so should be some maybe so So, okay, so how do I get from here to there? So, essentially what you're doing here is you're gauging the Z2 symmetry. Summing overall gauge field here, and with some weights. And that's how to get there. So the question is, okay, what's the analogous thing in 2 plus 1 dimensions? Well, or vice versa, sort of gauge, if you wish, fermion parity that you get to here. Now, if there is something like this to be put here, then again, should be there's some quantity which tells you whether something is even, whether fermion is an even part of fermionic ground state, or the fermionic space of states, or odd one. But there's a whole Riemann surface here. So the analog of this, so natural guess means that we need to start with the bosonic system, which can be coupled to a background gauge field, which is a 2-form. Well, more precisely, class. Well, this called is two-dimensional spatial side like sigma. Maybe you should have some background field like that. And when you gauge it, the symmetry, this B can fluctuate. You can have a sector where B is 0, integrates to 1, and when it integrates to 0. Those will correspond to sectors like Hilbert space and the fermions, where the fermion number is 0 or 1 or 0. So you want to identify somehow -1 to the f for the fermionic theory with the integral of B. That's one intuitive decision I believe that you want to couple. If you have some one-form symmetry, which can be coupled to a 2-form gauge field, then you can maybe turn the system into a fermionic system. And another thing we can look at now is so the fermionic space, the fermionic Hilbert space should be well defined for any spin structure. In the bosonic case, there's nothing like this. There's no just orientation. It's positive. It's oriented theory, but there's nothing else than orientation. So how does it appear? How do you decompose the Hilbert space obtained by gauging this symmetry into sectors for different spin structures? That's where the anomaly comes. So the general statement is that anomalies anomaly in any symmetry typically lead to the projective action of the symmetry in the Hilbert space. Suppose our if we don't have anomaly, then what is the one-form symmetry? One-form symmetry, one-form Z2 symmetry acts by some unitary residual in the Hilbert space. But this unitary depends not on the group element, but rather on the element of H1 over the manifold of the group. So there's some, say, gamma here, lambda, which lives in H1 of the group. So the manifold, which is the very small group, which now is Z2. More generally, you can have some other ability to look here. In our case, it's Z2 symmetry. So I remind you that for usual global spin transformation, the parameter is element of the group, which you can think of as element of H0, sigma greater than Z2. Here it's H1. So what does it mean to project it? Well, actually, imagine composing these guys, and in general, we can have some phase. And okay, so what are the obvious choices which come to mind? There should be some phase made out of two degree 1 cohomology classes, living on the two-dimensional Riemann surface. The most obvious choice for this omega would be simply this. There's second form of this one. Now you can approach it more abstractly. You can ask, okay, how many possible anomalies are there? I can just ask this question. Turns out that just classify all possible anomalies can happen. Well, in general, if we have a symmetry, you can classify possible anomalies. It's possible. It's called Lezino consistent condition. So, turns out that if you look at three-dimensional space-time and one-dimensional symmetry, then possible anomalies are classified by Z mod 4. And that's actually twice the generator. It's one of the most elementary anomalies in some sense. It's twice the elementary anomaly. But that's the one we need. So why do we need this anomaly? Well, because I mentioned, so we have this, so when I gauge a symmetry, what does it mean? Well, first of all, I'm allowed to turn on now this gauge field. But second, I also have to impose Gauss law, which means I have to project to gauge invariance states. In particular, you can look at transformations which leave this B unchanged. Suppose you look at sector with B equals 0. So B transforms like this in the transformation in general. In particular, these are transformations which leave this B just 0. Namely, if the lambda is closed, in general, lambda lives here. If it's closed, it's a cycle, then it gives B invariant. And when you impose this condition that your states, say for B equals 0, and then it's under this U lambdas, right? Now you cannot actually do that because you can have this non-trivial extension. You cannot require the state. You cannot require your state to be literally invariant, right? That does not even work. If you want to say it is 0, right? You have this non-trivial extension. But you can try to remove this projectivity by redefining your lambdas. You can try to define maybe U prime, well, U hat lambda. Because U lambda comes some fine function, or maybe rho of lambda. And you can try to tune this rho lambda so that this new guy satisfies the usual law, right? Without any projectivity. So you can easily check. Like, so for this to work, you must have this conditional rho. One of these. Well, we want half of this. So, well, we know what this is. It's this quadratic function which refines the intersection. And we know that such things are labeled precisely by spin structures. So this guy, there's many of these guys, there's many ways to do this as there are spin structure with sigma.
So if you think about it from the fermion side, you want to have all the spin structures, and if you think of it on the boson side, you have all of these.
Yeah, so basically you look at different versions of the Gauss law. Like you impose this, in other words, condition, the modified one. That we call this quadratic function of the Q. We're going to impose this condition. Or H is the spin structure. So in other words, I have this big Hilbert space for 0 integral two-form gauge field, and then decompose it to sectors like this. I only look at states which satisfy this condition, and it's for each spin structure, that gives me all components of the fermionic Hilbert space.
So can I think of the spin structure as basically describing, and I can imagine having sort of Z2 fluxes going through all of the holes of the manifold. Can I think of it that way?
Yeah.
And can I think of that as being the Z2 gauge field on the other side?
No, well, no. Here is two forms of gauge field, right? So,
Nice.
so this is like magnetic flux, and these guys are like electric fluxes. So anyway, so that's how you get from bosonic side to the fermionic side. So that suggests that to construct a fermionic system, you just consider with a bosonic system and gauge with a suitable anomalous one form of symmetry, anomalous in this way. And then just gauge it in some deformed way, because you cannot usually gauge it with anomalous, right? You can gauge it once you introduce spin structure. projected to this state. And then we get fermionic system. What's not clear here, of course, whether the resulting system is actually local. We start with a bosonic system, but why is this a local fermionic system? So to actually show that, we need to work harder. So turns out that one can, instead of doing this, which is not very, well, this is a numerical function of lambda, which doesn't seem like a very good idea. Instead, you can do the following. You can tensor this system, this Hilbert space, with a Fock space of sort of spectator fermions. And define, instead of doing this, I can do the following. I can define this two hat lambda, so this is actually it's too naive. Rather, I want to do the following thing. There are some hopping operators made out of fermions. And I call them S lambda. And lambda, well, lambda is a one per cycle, but if I sort of dualize the picture, it can one cycle. So there's some path, closed path on my graph in the sigma. And if I make product of fermion by lineage, and hop fermions inverse of the graph, I'm going to get some operator with some particular convention. And it turns out that another way, more physical way to sort of resolve this projectivity is to form this product. So define u lambda to be u hat lambda to be u lambda, and it's fermionic. And further, I want to impose a condition. The fermion number on every vertex, the square graph is equal to the B field there. So it is reminded, so there are two dual pictures, the triangulation, and B can be thought of as a function of two simplices. And the dual picture is a graph. So B can be thought of either living on this plate of the triangle, so the triangulation, or on the vertex of this graph. And my fermions also live in the vertex of the graph in my dual lines. So I can say, well, in every vertex is going to have two-dimensional Fock space. This is represented with the Clifford algorithm with one generator. And I'm going to force the constraint that whenever B is 1 here, I should have fermion number 1. That should be excited state of this single two-dimensional Fock space. Whenever B is 0 here, I'm going to have ground state. Fermion number 0, that is ground state.
So is this anything related to the flux attachment?
It is basically a version of flux attachment.
And there was always this problem that the charges live on the direct lattice and the fluxes live on the dual lattice. And so how do you decide?
I think
You're sort of able to
there's no problem.
get around that?
Yeah. So the point is that spin structure something takes care of it. Because, so here with only one lattice, it's triangulation. So we just work on this triangulation distributions to try out the graph.
I see. So it's the spin structure is the missing ingredient in the flux attachment.
In fact, you can look at some papers which vaguely say that spin structure is some association of a vertex to a triangle or a vertex to a quotient. There's a paper with Francis. That's basically what it is here, in some sense. But it's made more precise. So the point is once you choose. So the definition of this S lambdas. So we form these guys, because S lambdas also, just like these factors, which depend on spin structure, these guys also need some sort of signs. Once you do that, these new guys satisfy the usual non-projective relation. Literally like that. And then you can impose the usual Gauss law. Okay. So that's how you literally fermionize a bosonic system with this method. You impose also the constraint that whenever B is non-zero, there's a fermion there. And furthermore, you project on this using this Gauss law. Okay, so the simplest example of such a bosonic system is actually the toric code. So toric code is Z2 gauge theory, most trivial Z2 gauge theory in 2 + 1 dimensions. I can describe it many different ways, but one way is to be an action. So we have like we have a gauge field which lives in a chain in my 3-dimensional manifold. efficient. It's a Lagrange multiplier. With some actions like this. That's called the two-gauge rhetorical. You can explicitly quantize it on any spatial slice once you choose a triangulation. And explicitly write out these operators. Actually, there's several one-form symmetries there. But there's one particular, some of them are non-anomalous, but there's one which is anomalous and presently has this relation. It's in this they are written out of the table. And then you can apply this thing. And in that particular case, it gets in a very boring formalized system. You get a unique state, for instance, sort of a trivial fermionic phase. But in particular, that's without any global symmetry. But that actually provides a way to construct all the slightest models to sort of try to cluster before using physical mechanics. You start with this system, which already know gives you a fermionic system with a unique ground state in spatial topology, and couple it to background gauge field, some sort of external gauge field, for some finite symmetry group G. And then essentially guaranteed then you're going to get one-dimensional verse space after fermionize. This system has, of course, the generous when once you fermionize, you're going to get unique state related to the structure. So, and that's true even if you couple it to background gauge field. And you can show that that guy gives rise to all this fermionic short-range phase I talked about before. It gives kind of lattice construction of all the spaces that are classified for using spin cobordism or whatever it's called. And one can also describe the reverse transformation. It's kind of interesting to me. So with the fermionic system, try to get some bosonic system out of it. That's nice. It will be nice to see what you get because, say in the two-dimensional case, the quantum one-dimensional case, very simple fermionic system, you write some pretty tricky bosonic systems. Like you have started with, say, free fermion and get Isaac model, which is not trivial. So now here in bosonic, its transformation is kind of complicated. So you start with some free fermion, first we get some bosonic system out of it, but it's quite horrible. So I don't know if it can simplify it and give some interesting bosonic system, which is secretly equivalent to free fermions. So but nevertheless, the lesson of this is flux attachment always works if you do it right. For example, it can be extended to say 3 + 1 dimensions. And then we're going to have, instead of a 2 form, we're going to have a 3 form gauge field with relevancy 2. And can similarly bosonize fermionic systems. Same idea.
Questions?
So this doesn't give any insight into the three-dimensionalizing model, does it?
It shouldn't, in principle, right? I mean, not well. You can try to fermionize it and see.
Right, that's what I'm saying. Maybe it's
Say this transformation is very complicated, unlike in 1 + 1 dimensions. So, I haven't really tried. Maybe one gets something interesting in the system, but it's not only free, that's for sure. And I think the reverse is more interesting. For preferring systems, map some complicated-looking bosonic systems, which sort of therefore become soluble. The problem system is nobody ever looked at because they're so horrible. But, maybe not. Maybe there is something. Maybe there are later something more coming.
What goes wrong in 5 dimensions?
Nothing goes wrong. It's just that there is this oriented cobordism deviates from covariant oriented cobordism deviates from a covariant cohomology. That has to do with the following fact. If you have like 4 space-time dimensions, there's an argument showing, suppose you have QED, like theory of U1 gauge fields, like Maxwell theory, which has monopoles and charged particles. It's usually said there's no consistent, it's not very consistent to postulate that both monopole and charged one particle are fermions. So there's some anomaly, right, to that. if you imagine that your four-dimensional system with the boundary is only 5 dimensions, then actually this anomaly is kind of not there. So that is, this bosonic system in 5 dimensions, whose boundary supports something which is very different from a purely four-dimensional viewpoint, namely the theory of electromagnetism, where both monopole and electrons are massive and firm, are fermions. That's why it's there. It's there to regularize the theory with both a fermionic monopole and with
And what's the statement just in terms of cobordism?
well, just that there is a the SO, the Bordian group of so there are the cobordism, degree 5 cobordism of a point movement body symmetry, just bosonic system without any symmetries, is Z2. And the reason it's Z2 is because unique number can compute for the cardinal manifold, which is what is invariant, namely integral of W2 up W3 to the I times this is a candidate partition function for some physical system. I can actually write some concrete lattice model which gives that as a partition function, using this bosonic theory. It's interesting because, well, it's interesting from the theoretical viewpoint. There's about 5 dynamics. It's the first example. Well, originally when people tried to classify bosonic phases, they would use this group cosmology approach. That's the whole thing. It's not, but it's one of the first examples where it's like this.
Any other questions? And then on again.